Welcome everybody. We're continuing with section 5.2, and now we're getting into some properties of inner products. Now, these properties are going to. So let's just backtrack for a second. We have here. This was the definition of an inner product, and we're going to examine some properties. Now, if you notice that the properties, let's see, 0, comma v is equal to v, comma 0 equals 0. Now this is definitely true of dot products, but we're not looking just at the specific dot product. We're looking at general inner products, and as I said, general inner products are defined. A dot product is sort of like a role model, or a poster child, for a, what I'm saying, for a inner product. But an inner product can be more general. Anyway, let's look at some of these theorems. A lot of these will sort of what's the word, reflect or what we've seen before. So u plus v comma w is equal to u comma w plus v comma w. U comma cv is equal to c times u comma v. Now, 2 and 3 sort of follow immediately, really, just from the commutativity of a inner product, because inner products are commutative. So basically, it's taking number 2, and it's just switching it around, and we're also taking number 3, and we're kind of switching that around. So getting the second part of the theorem, the third part of the theorem, that kind of follows the commutativity. The first part is a little more interesting to me, and it's looks obvious, but it's really not so obvious. That's saying that 0 comma v is equal to v comma 0 equals 0. Now remember, the 0 over here is the number 0, the scalar 0. The 0 over here is the vector 0. It's a 0 vector. Now it looks a lot like the number definition 4, that if vv is greater than or equal to 0, and v comma v equals 0 if and only if v equals 0. So we're saying here, v comma v equals 0 if and only if v equals 0. The thing is, that's not what this is. That's true, but it doesn't. But what we have over here is not quite the same thing, because we're not talking about 0 comma 0. We're talking about 0 comma any vector. So 0, not just in other words, in the definition we said that 0 comma 0 equals 0. But now we're saying, this theorem is saying that 0 comma any vector is going to work. And to prove the theorem, we're actually going to use condition 1 and condition 3 to prove this. So let's look at the proof. So first we're going to say 0 comma v is equal to v comma 0. So we're using that. That was definition number 1, and we're using that really just to say that these two problems are the same thing. So if I prove this, or if I prove that, then I got it all. In other words, if I prove 1, I got them. If I prove 0v, that automatically gives me v0. Or if I prove v0, that automatically gives me 0v. Anyway, next. So that's out of the way. And we know from the definition, I'm sorry. So we also want to use the fact that 0 times any vector is equal to the 0 vector. That means that, let's look at 0v. So 0 comma v, well, I could replace that's the 0 vector, which is in the theorem. The 0 vector, I could replace that with the scalar 0 times the vector v. And we know from definition number 3 that I could take the 0 out. I could take the scalar out and put it over here. And again, that was just number 3 in the definitions. And now I have 0 times v. Now, so whatever v comma v is, it's getting multiplied by 0, and my final result is 0. So we see that 0 comma v is equal to 0, and that's a very slick and very awesome proof. And again, it was something that looked kind of obvious, but it really was less obvious than it appeared to be. We actually had to go through a bit of work to prove that. Now, I want to talk about this idea of length, distance, and angle. Now, again, we you have to be aware that we're not doing regular dot products and not doing regular Euclidean n space. We're not using regular space. These vector spaces could be anything. So so even though the terminology is going to look very similar to what we've seen before, the meanings of these things might be quite different, and that's just the way it is. So, in other words, we see here this symbol right here for the length of a vector. We had learned it that it was the square root of Pythagorean theorem. We learned it a certain way for R2, R3, Rn, whatever. This is not R2, not Rn. This is. I mean, it could be, but it may not be. So therefore, the length of a vector, which we use this symbol that we used before, but now the symbol is going to have a different meaning. It's going to be the square root of the inner product of u and u, not the dot product necessarily, but the inner product or whatever that might be. And the distance between u and v, which we call a d of u and v, that's going to be the length of u minus v, but the length may or may not be the typical standard concept of length that we have from R2 or R3 or Rn. It's this length here. This is going to be this is going to equal to the square root of u comma u. So I'm just trying to point out that it's wonderful that these definitions all look like what we've seen before, and that's a good thing. But we're applying it now to a whole different creatures. They may have nothing to do with anything we've seen before. They're just totally random, vector spaces. But assuming they are vector spaces, and assuming we have an inner product which satisfies all the conditions and definitions of an inner product. Anyway, the angle between two non-zero vectors, u and v, that's going to be given by this formula. We're going to look at now. In the past, we had the dot product u dot v over the magnitude of u and the magnitude of v times the magnitude of v. But here it's not. It's similar, but it's not necessarily a dot product. It's whatever the inner product is. So it's the inner product of u and v over the length of u times the length of v, which may or may not be the same kind of thing. Again, I know it sounds like a broken record, but I want to point out that the kids now even know what that means, broken record. Anyway, I want to just emphasize that. And of course, theta is between 0 and pi. And we're going to have to, well, I'll get to that. Number 4 of our definition is that u and v are orthogonal when not the dot product equals 0, but when the inner product equals 0, whatever that inner product might be. A couple other things. If the length of a vector is 1, then we call it a unit vector, just like we did back in Rn, back in the good old days. And also when if I take a vector and divide it by its length, I get a unit vector. And it's a unit vector in the direction of v. Again, even though these aren't the same little arrows that we're used to, but as we'll see, we're going to do examples. Finally, we have to in order to say that cosine theta is equal to this thing here, that means this fraction, this giant fraction, has to be in between -1 and +1, and which who says that that's going to be true? But we're actually going to be able to show that with the Cauchy-Schwarz inequality. Now we did the Cauchy-Schwarz inequality just for regular Rn. Now we're going to prove it later for general, inner product vector spaces and all that kind of cool stuff. All right, so let's find some inner products. So here we have polynomials. So this is Pn. This is all the polynomials of degree n or less. So we have one polynomial p, and that's a0 plus a1x plus a2x squared plus anx to the n. And then we have a second polynomial q, which is b0 plus b1x plus b2x squared plus b3x x to the third plus bnx to the n. Typical thing. And we're defining the inner product as follows, that P, if I take P and Q, the inner product is going to be A naught times B naught plus A1 times B1 plus A2 times B2 plus dot 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 plus AN times BN. And that's the inner, that's how we define the inner product. And notice this inner product reminds me a little bit, if you know, you could really think of this polynomial as just a like Rn, like as an n tuple of the coefficients. So it's kind of like, so the inner product here is very similar to the dot product in a normal situation. Anyways, we want to, and by the way, I'm just telling you this is an inner product. You have to, you're gonna have to show me that it is actually a, or you're gonna have to show yourself, you know, that it actually does satisfy all the inner product laws. Anyway, we're going to take two particular polynomials. P of x is going to be 1 minus 2x squared. Q of x is going to be 4 minus 2x plus x squared. And then we're going to take a third polynomial, R of x equals x plus 2x squared. And we want to find the inner product of P and Q, the inner product of Q and R, the length of Q, and the distance between P and Q. So that's given for these particular P's and Q's. So I'm going to let you pause the video and work it out. Okay, time's up. Now that's enough pausing. Now we're going to solve these suckers. So the inner product of P, actually let me scroll down a little bit so you can see the original thing. The inner product of P and Q is, well, oops, here is, so I'm taking the 1 times the 4, that's going to be 0 times -2, and then -2 times 1, which is all those numbers right there. And if you crunch that out, you get 4 minus 2 equals 2. Now the inner product for Q and R, that's going to be 4 times 0 over here, then -2 times 0, which is again is just 0. So far I got nothing here, and then we have I'm sorry, -2 times +1. So we do have something with -2, and then 1 times 2, which is 2. So we get -2 plus +2, which are these numbers right here. 4 times 0, -2 times 1, 1 times 2, and that equals 0. So we're all good. And the length of Q, well, that's going to be the square root of the product of Q with itself. So if we take Q, the product of Q with itself, it's basically going to be 4 squared plus -2 squared plus 1 squared, which is 16 plus 4 plus 1, which is 21, square root of 21. So the length of Q, whatever that means, the Q is a polynomial. So what do you think of, what does that mean? What does it even mean? But we're defining it. That's why it gets a little abstract. You know, you don't, if you try to think what does length mean, you may drive yourself crazy, but whatever, but this is the abstractness. And okay, I don't want to talk too much. I'll just make things worse. Sometimes the more I philosophize and pontificate, the worse I make things. So let's move on. And finally, the distance between P and Q, well, that's going to be the length of P minus Q. So P minus Q is just the right standard thing. Just take this polynomial, subtract that polynomial. That's something you know, and you wind up with -3 plus 2x minus 3x squared. And now you want the length of this based on our definition. And the definition that we particularly had was sort of similar to a dot product definition. We already established it up above. That's -3 squared plus 2 squared plus -3 squared again, which is 9 plus 4 plus 9, which is 22, but it's the square root of 22. So the distance between these two polynomials is square root of 22. Huh? What is it? Distance between two polynomials? Huh? What's going on here? Well, that's the story. That is the when you make inner products, that's what you have to get used to. That you know, you may wind up having concepts. If you try to picture them, you go crazy. If you just take it for the math or take it for the functionality, you know, it'll. I find that helps. So just think of anyway. Moving on. Notice that P and Q, their dot product is 0. So P and Q are not orthogonal in our by our definition. But what if I would keep the same P and the same Q? Let's say I'm looking at the vector space Pn, and I have the same P and the same Q, but I redefine what the inner product is. So I redefine the inner product as A naught B naught plus A1 B1 plus 2 A2 B2. See, before we just had just A2 B2. Now I'm putting in that extra little 2 over there. So what would happen there? Well, let's look at P and let's look at Q. What would happen? Let's just do P and Q. You'll get the idea. You can do the rest yourselves. So for P, I get 1 times 4 plus -2 times 0. So far I have 4 plus 1 times -2, but I have to double it because we added that extra 2. So I get -4. So I wind up getting +4 plus -4, which is 0. So with this new inner product, P and Q now are orthogonal. And that's something you got to realize, that it's not just the vector space, but it's how you define the inner product. And if you define the inner product one way, certain vectors may be orthogonal, and if you define the inner product a different way, certain vectors, different vectors, are going to wind up being orthogonal, and so on and so forth. Okay, let's look at another really cool example, and that is using an inner product on C01. C01 is all the continuous functions or looking at all the continuous functions from defined in the interval between 0 and 1, and we're going to use the inner product defined in example 5. And to refresh your memory, that was example 5 right there. And the inner product of function f and function g, the inner product of function f and function f and g, these are two different functions. Their inner product is f of x, is the integral of f of x times g of x, and from a to b. And of course, a for us is going to be 0, and b for us is going to be 1. But this is how we're defining the inner product. And now we're gonna. So we want to, with this definition of inner product, and given that we're going to let f be x, and g of x is going to be x squared. So f of x is going to be x, and g of x is going to be x squared. And we're looking at C0, 1. So we want to find the length of f, which is length of a function. What does that mean? The length of f and the distance between f and g, which, what difference between two functions? The distance between two functions, what does that mean? But we're going to give it meaning. It's going to get meaning today. So f of x equal to x. So the length of f squared, that's just the inner product of f and f in itself, which by our definition is going to be integral from 0 to 1 of f times f, or in this case, x times x, because that's what f is equal to, which is the integral from 0 to 1 of x squared, which is 1/3. And that's something you know simply from calculus, right? It's x cubed over 3, evaluate between 0 and 1, and we're good. So it's 1/3. But that is the distance squared, the length squared. So the length itself is 1/√3. Now, the distance between f and g. So remember, f of x equals x, and g of x equals x squared. The distance between them is as follows. Well, the distance, again, by definition, is going to be the distance is going. Well, we know that the distance squared is the inner product of f minus g and itself. And again, we have that from R, and that's equal to the integral from 0 to 1 of f minus g times f minus g, or f of x minus g of x. When I say f and g, I mean f of x and g of x. But f of x is x, g of x is x squared, and we're squaring it. So we have here If we square this, we get x squared minus 2x cubed plus x to the fourth. Just multiply that out. And the integral of this, the integral of x squared is x cubed over 3, and so on and so forth as basic calculus. And we're going from 0 to 1. This winds up being 1/30th. Work it out, it's 1/30th. It's actually 1/3 minus 1/2 plus 1/5. So it all works out to be 1/30th. But that's the square of the distance. Because remember, the distance was the square root of this product. Anyway, we have to now, that's the square of the distance, so the distance itself is 1 over rad 30. 1 over rad 30. And which is awesome. And I just want to point out that we talked about the distance being 1 over rad 30, which is approximately 0.183, in case anyone was wondering. And again, what does it even mean? So in practice, the distance between a pair of vectors is not as useful as the relative distances, because, what does distance mean? But relative distance makes a difference. So for example, if I would have used g of x is x squared, which is what I had in the previous example, but instead of looking at comparing g, so here we compared g and f, and we got, we got 1 over rad 30, which is, 0.183. What if I took the same g and compared that with h, which is x squared plus 1? Well, if I would go do the whole smack here, I would get this distance to equal 1, and it's not that hard to do, just do all the same stuff. And that means that the distance between f and g is 1 over rad 30, whatever that means. And the distance between g and h is 1. Now notice that 1 is bigger than 1 over rad 30. By the graph, these two functions do look further apart. Exactly what these numbers mean, again, it may or may not always have simple meaning all the time. One last thing for this video, the properties of length and distance listed for Rn in the preceding section also hold for the general inner product spaces. So for example, if u and v are vectors in an inner product space, then the following is all true. The length is always going to be greater than or equal to 0. The length of a vector is going to equal 0 if and only if the vector itself is a 0 vector. I could pull a constant out of this, and I get c times u, because it becomes absolute value of c. So the length of cu is c times the length of u. Like again, these are all things we saw in Rn, but these are all going to apply in regular. The distance between u and v is always going to be greater than or equal to 0, and it's going to equal 0 only when u equals v, and of course commutative. So these are all properties we saw in Rn. They also apply over here, and that concludes this video. We will see you again in the next video. Bye bye. Have fun.